Okay, so last video for the convergence and divergence test packet. This is going to cover ratio and root test. Ratio test is the more important out of the two. The root test that we'll do quickly on the next page. It's not even on regular AP exams, so for sure you don't really have to worry about it. It's kind of neat to know because it's applicable and helpful in some situations, but anything that you wanted to use the root test on, you could have also used the ratio test on. Just sometimes the root test is easier. But anyways, ratio test, pretty important test. It's pretty easy, a lot of algebra, but let's go through it. Now notice this ratio test is going to work especially well whenever you have factorials. Those are the little exclamation points. And as well as exponentials. Those things that algebraically don't reduce super well all the time, those are going to work really well with this ratio test. Let's read the test. It says, let you have some infinite series be a sum of non-zero terms. That's great. It says 1. The series converges absolutely, so you don't have to worry about conditional convergence. It's going to safely converge, right? It's going to be finite enough so that even if you made some of it negative and made it, or sorry, if you made it all positive and made it even bigger, it would still converge. So it's going to converge, and you know it's going to converge absolutely if, here you go, you're going to take a limit as n goes towards infinity, and you're going to take a limit of a ratio, hence why it's called the ratio test. Now what you're going to need to do is put a sub n plus 1. That means you're going to go to your formula for your series, and you're going to plug in n plus 1 everywhere you see the n, right? So you're looking at the next term. So you take that n plus 1th term, and then you're going to divide it by the nth term. So basically you plug in whatever your formula was, that goes on the bottom, that's your nth term, and then the n plus 1, the next term, goes on the top. And you're going to look at that ratio, apply the limit as n goes towards infinity, and the relationship between that limit value and 1 is going to dictate what's going to happen. If you do the ratio test and that ratio ends up being less than 1, that's going to converge. And think about it. If you have a ratio and that ratio is less than 1, that means the top is smaller than the bottom. That means the terms are going to get smaller. The absolute value just means if we have negatives, it doesn't really matter if it oscillates. But really you're just looking at, hey, if this next term is always smaller than the one before it specifically, and this ratio test is going to work, and I get this ratio, n plus 1 on top, n on the bottom, that ratio is less than 1, it's going to converge. And it converges absolutely. However, if the ratio test gives you some number bigger than 1, like 2 or 50 or infinity, you know that series is going to diverge. So smaller than 1 converges. If it's bigger than 1, diverges. If the ratio test ends up giving you exactly 1, then the ratio test is inconclusive. It doesn't mean converge, it doesn't mean diverge. You don't really know. It could still converge, but it would only be conditional convergence, or it could potentially still diverge. The only thing you really know, if the ratio test is 1, it's not going to converge absolutely. It could still converge conditionally, or it still could diverge. But you really don't know. If the ratio test is 1, then you really shouldn't have been doing the ratio test. It's probably a geometric series test or some alternating series test that you're supposed to be doing instead. So less than 1, converge. Greater than 1, diverges. If it's equal to 1, rut-row. You've got to do one of the other tests. All right, look at the two examples we've done here. See if I can scroll it. Here's the first one. So again, it gives me this series. That's not something I can do the integral test with. That's not geometric. It's not going to alternate. So you have to figure out what test can you use on that given series. And the ratio test ends up kind of getting used quite often. So here we go. Remember, this original thing, that's the nth term. That goes to the bottom. And then you change all the n's to n plus 1s. And then that goes to the top. So n plus 1 on top, n on the bottom. And then you're going to evaluate that ratio as n goes to infinity. Absolute value. So if there's any negatives, they just go away anyways. Right, so now let's look. I'm going to do the sandwich trick. Remember, everything in the middle sandwiches together. It goes to the bottom. The outside two layers, they multiply together. They go to the top. And I try to align the common terms over each other. Like here I've got the exponential term with the base 2. And then I've got the factorial terms. If you try to just vertically align them, it'll help you reduce. Here I have 2 to the n plus 1 on the top. 2 to the n on the bottom. Those are going to reduce. But there's going to be 1 power of 2 left over on the top, right? That's the bigger bigger exponent, so you're going to have 2's left over on the top. When you do your subtraction, n plus 1 minus n, that's just 1. So the 2's are definitely going to cancel. There's going to be 1, 2 left over, and it would be left on the top, which you can see here. And then you look at the factorials. Hopefully you can remember how to do some algebra with your factorials. You find the bigger factorial on the bottom, you expand it enough so that it reduces with the top, and then you're going to be good to go. This is the bigger factorial. It's going to expand a little bit, and then it will cancel. But all this stuff, it's going to reduce to 2 over n plus 1. And then you're going to apply the limit as n goes towards infinity of this chunk. Since you have n's on the bottom, you plug it in, you would have infinities on the bottom. And if the denominator gets really, really, really big, fraction overall gets small to 0. So here I applied this ratio test. I did the limit, nth plus 1 term on the top, nth term on the bottom. That limit ended up giving me 0, which is less than 1. So I know that series is going to converge by the ratio test. I know it also converges absolutely, but it's going to converge by the ratio test. Okay, let's look at the next one. Okay, so here we go. I think that's on the camera. Let me check. Yeah, it looks pretty good. Here we go. We've got this original series. Again, not something that we really could do any of the other tests with. Ratio test is going to get it done, though, pretty easy. The nth term, just copy this sucker exactly. That goes to the bottom. Then you put the n plus 1, right? So we have n plus 1 squared. Then you have n plus 1 plus 1. That's why this is now n plus 2, right? You changed the n to n plus 1. So you had n plus 1 plus 1. That got you the n plus 2. Then you're going to have this 2 to the n plus 1. So the original thing goes on the bottom, however this is, you just copy it. Then you change all the n's to n plus 1's, and then that goes to the top. Then you're going to apply that limit as n goes towards infinity, see what the answer is. Remember, sandwich trick it first, so the stuff in the middle all goes to the bottom, outside 2 layers go to the top, and then if you kind of vertically align the kind of similar pieces, it's just going to help you see what cancels and what's left over and which layer it's left over on. Here you look at the 3's, looks like the exponent on the top is bigger, so you're going to have 1, 3 left over on the top. Look at the exponentials with the 2's. Looks like you're going to have 1, 2 left over in the bottom. Now here, those don't cancel, right? Those aren't factorials. Those aren't going to expand and cancel. So those things just kind of stay as they are right now. You have that n plus 1 in parentheses squared over n squared. Now really, the 3 and the 2, that doesn't have anything to do with the limit, right? The limit is just as n goes towards infinity. So the limit is definitely affecting these 2 terms, but what we can do is take those non-n terms and I can factor them out, which is what you see on the next line. I think that's still on the camera. Yep. So I got the 3 over 2 factored out, and then I'm just working the limit with the chunks with n's. So I have n plus 1 squared over n squared, which the limit of this, since if you were to expand it, you'd end up having n squared plus 2n plus 1. You don't have to expand it, but it would be degree 2 on the top, and it's a degree 2 on the bottom. And since those powers are the same, then the ratio of the diluted coefficients, 1 over 1. So you should be able to do this limit pretty quick. Since they're both powers of 2, you would just look at the ratio of the coefficients. This limit, though, is going to end up being 1. 3/2 times 1 is 3/2. That's bigger than 1, and when the ratio test ends up giving you all this work bigger than 1, you know that series is going to diverge. So pretty easy test. You need to remember, though, that n plus 1 goes on the top. Oh, there's a third one. N plus 1 goes to the top, and then n goes to the bottom. I forgot there was a third one. Okay, let's see. Can I keep it on the camera? Hopefully. So this last one, again, n plus 1 term, so you have n plus 1 plus 1, so that's n plus 2. Then you have your 3 to the n plus 1, so n plus 1 term on the top. Then you just copy this original thing. The nth term goes on the bottom. You apply the ratio test. I always try to sandwich it down first, so the middle 2 bottom, outside 2 top. Those are the factorials, so they're going to kind of reduce against each other. That one's the bigger factorial, so it's going to reduce and have stuff left over on the top, and n plus 2 on the top. Here are the exponentials with base 3. It looks like you're going to have a 3 left over on the bottom. So here we go. If you want to, you could factor out the 3. You don't really have to though. As n goes towards infinity, you'd have an infinity over 3, which would be infinity. Or if you wanted to factor this out, you'd have 1/3, the limit as n plus 2, as n goes to infinity. That would still be infinity though. So either way, if you want to factor out the 1/3, or if you just leave the 3 in the bottom in there, it doesn't really matter. This limit will end up being infinity, which, spoiler alert, is bigger than 1. So that one's also going to diverge. So ratio test, pretty easy. N plus 1th term on top, nth term on the bottom. Then you just reduce it, evaluate that limit. If the limit ends up giving you exactly 1, you're stuck. You don't really know what's going to happen. You should have been doing one of the other tests instead. Okay, and then quickly we'll do the root test as well, just for your knowledge. It's not the most important of tests. In fact, it's probably right there with telescoping, one of the least important tests. That's okay. The root test means instead of doing a ratio and applying the limit, that's the ratio test, we're going to end up taking the nth root of some expression, and that's the root test. And it's basically the same rules as the ratio test. Whenever you take the nth root, you're going to apply the limit as n goes towards infinity. If you get less than 1, converges, absolutely. If you get bigger than 1, diverges. And if you get equals to 1, then that's inconclusive, right? So you should have been doing one of the other tests. You don't really ever need to use root test, because anytime root test could be used, you could have done the ratio test instead, but sometimes it's easier to do the root test. Okay, so let's look at, I think this is just 2 examples. First one, now here I've got e to the 2n over n to the n power, so that's interesting. Noticing though that they both have n's as part of the exponent, so if you take an nth root, it's going to simplify and make that expression quite a bit easier. Again, you take the absolute value just to kill any negatives that are there, but I'm going to take the nth root of that original expression, then evaluate the limit as n goes towards infinity. Here we go. If I take the nth root of e to the 2n, well, the n and the n would cancel, leaving you just e to the 2. Here, if you have the nth root of n to the n power, the nth root and the nth exponent would cancel, leaving you just the n. So seeing how both of these had n's as the exponent, the nth root cancels those really quickly and easily. And then we just end up having this, the limit as n goes towards infinity, e squared over n. Clearly, that's going to be infinity on the bottom. E squared is just a number, really small number. So if you have e squared over infinity, 0, which is less than 1, which means that series is going to converge. Converges absolutely, but it's going to converge by the root test. All right, last one. Here we go. Again, oh, this one, look, like it's just begging for you to use the root test. Look, it's all to the nth power. You could use ratio test if you want, but you just have more algebra to do if you did the ratio test. Here, since everything is to the nth power, I think the root test is kind of just screaming right at you, hey, please do the root test. Anyways, look at it. Apply the nth root to this original thing. Again, you would kill the negatives, just take the absolute values, doesn't matter. If I take the nth root of that original expression, the nth root and the nth power are going to cancel, leaving you just all the stuff that was inside the parentheses. That limit of 3n plus 4 over 2n, that limit's just 3 over 2. 3 over 2 is bigger than 1, so it's going to diverge by the root test. So there's your last 2 tests. Ratio test is important. It comes up quite a bit. I don't think it's very hard. There's quite a bit of algebra that goes with it, but it's pretty easy. Root test, less common. Again, anytime you want to use root test, ratio test would also work. It's just sometimes root test gets you to the answer a little bit faster. All right.